Okay, welcome back. And as you may see, I changed our microphone setting. Actually, I hope you will hear better now. Right? I hope. Probably it's better. Okay. Anyways, so let's see. Now our next problem is about partial derivative. Right? Let's see. Now we have a function, and we are going to compute, if they exist, of course, their first and second, partial derivative with respect to first variable and the partial derivative with respect to second variable. Okay, fine. So let's see. Solution. Okay, of course, the question is about differentiability around the point 0, 0, but this is a very general trick. If you look at carefully, 0, 0 is a kind of a problematic point in the sense that the behavior of the function f changes around the point 0, 0. Therefore, 0, 0 is a kind of a jump point. So note that the behavior of the function changes around the point 0, 0. So we should use the definitions. So we should use the definitions. Okay, of course we should remember the definitions. Maybe a quick recall is the following. We have this, for instance, okay, and we have some graph, whatever it is, and we have our point A, B, right? That point and that point. Okay, and we have this point as well. So everything is nice. So and as you know, if you really want to compute partial derivative with respect to first variable, which means that the second variable turns out to be fixed, right? That thing. Therefore, we are looking for this curve, and if you consider this part, which means that the variable x can be viewed as a fixed variable, and then that means that in the image we have this curve. Okay, and then actually if you really want to compute for instance this line, and also we have another one, something like this. Maybe I should be careful. It's a tangent line, and the slope of this thing, right? I mean, this point, by the way, is just, if you look at carefully, okay, this point is a, b, and f of a, b. And if you really want to understand the slope of this line, slope is just f1 ab, and the slope of that thing f of 2 ab. Okay, and then we know that actually we will see soon here, of course, y fixed, if you like. This is x fixed. Okay, this is exactly y equals b. This is exactly the line x equals a. Okay, so this is the picture, and then later by using the suitable direction vectors, because you have a line, this is a tangent line to this curve, when you fix y equals b, and then you have another curve over here, you see another curve and another tangent line over here, right? And now by using the corresponding directional vector for those lines, then we can span a certain plane, which is called a tangent plane. Okay, soon we will discuss the concept of tangent plane, but at this stage this is enough. But later we will sketch some picture like this. Okay, anyway, so the recall is, if you really want to compute f1 ab, this turns out to be limit h approaches to 0. Since the second slot is fixed, if you like, so you want to understand change in the first slot. Therefore, you should remember the definition, limit definition of a derivative, right? And apply this definition for the first slot, okay? Over here, second slot is fixed, okay? And that's all. I mean, this will be the definition. And a similar story, just change the rows actually, and then you will see that the limit definition of this partial derivative turns out to be, now the first parameter is fixed, if you like, first variable is considered as a constant if you wish. Now you want to understand the change in the second parameter, h. Okay, I guess everything is fine. Now in our case, now let's check our case. So this is the picture. So in our case, let's see what we will have. Then of course, first observation, we really want to compute f1 0, right? And the limit h approaches to 0, so a is 0, therefore we have h, and the second parameter is 0, which is always fixed. And here is the definition. Now I'll just compute it. Since the definition of f is already given, just substitute. I guess this is 3, right? Sine, what was it? 1 over h squared minus 0, and divided by h, right? So let's see what we have. Limit h approaches to 0, sine 1 over h squared divided by, just small algebraic manipulation gives you something like this. But now, just a quick change of parameter. Type argument gives you something like this. Just let this thing to be, I don't know, t, for instance. And then this turns out to be limit, limit t approaches to infinity, sine t divided by t. Okay, and maybe we should remember this sort of inequality from the usual one variable calculus stuff, and you should remember the standard squeeze theorem argument, and then this turns out to be 0 by squeeze theorem with identity star, right? Because as t getting larger and larger and larger, this part approaches to 0, and this part approaches to 0, and this turns out to be 0. So everything is fine. Oops, sorry. Okay, second part. And now we are going to compute, okay, f2 0, and let's see what we have. Limit h approaches to 0. What was it? What was the? Okay, anyway, so let me write it down. Fh f0 and divided by h. But now this is relatively easy, because when x equals 0, so we have, and y is h. Is that correct? sine 1 over h squared. So everything is fine, and this part is 0 already, and we have h, and these are cancel out each other, and fine, this does not exist, right? Okay, I guess it's fine. Okay, that's all. So the best part of the story is you should remember really you should understand the meaning of derivative with respect to first variable and the derivative with respect to second variable. Okay, in just one variable case we don't have such an extra option, but now we have some extra ingredient when we pass to higher dimensions. Okay, and similar, and as we will see in the next problem, but then by using this f1 and f2 and those lines, and as I said, the direction vectors of those lines, we just span a certain plane in which all tangent vector attached to that specific point sit inside, and then actually this plane will be called, the tangent plane at that point. Okay, fine. Here's the next problem. Now next problem is about to understand really the tangent plane. Okay, the tangent plane. But of course I should sketch the previous picture maybe, or something else. So let me think. Okay, maybe I should sketch something else. Okay, let's say we have something like this, some object. Okay, in this picture, a certain surface. So let's say this second order quadratic equation defines a picture like this. Okay, and then we really want to understand, for instance, that point over here and here. So it's up to you. Okay, it doesn't matter. Now this is exactly the point AB, but now this is exactly the point A, B, and f of AB. Okay, use your imagination. So this is exactly B, this is exactly, okay, if you like, if you really want to more precise, this is 0B and this is A0. Okay, now if you really, maybe I should change our color. Maybe if you really move in this direction, and we have something like this, a curve like this, and if you really move in that direction like this, which means that when y is fixed, okay, we have something like this. I should, oops, oh my god, oh, okay, I'm sorry. What was the picture? Remember? Okay, anyway, some picture like this. Okay, anyway. Okay, let's consider this picture. No problem. And this is the other curve, so everything is fine. And then, as we discussed before, we have this tangent line. Like this, and we have the other one. Oh, it's not a tangent line. Okay, just a second. Okay, something like this, if you like. And then, as we discussed before, okay, so the slope over here is just f1 AB, and the slope over here f2 AB. Okay, this is the slope. But of course, when you discuss those things, we have a vector, right? So we have a vector like this, maybe a little bit, and we have another vector over here. Oops. Oh, okay, anyway. So we have some other vector here. Okay, and this is exactly what was the point over here. So this is our one of the vectors. Okay, and this is the tangent line. Okay, sorry. Okay, anyways, maybe I should skip those parts. So this is exactly the point A, B, f of A, B. Okay, so we really want to understand the tangent plane like this at that point. Okay, and of course, when you really want to understand the tangent plane, you need a normal direction. But of course, you can easily compute those vectors. Actually, those vectors are just, for instance, the first one. First one is nothing but this vector AB is 1, 0, f1, AB. This is the one of the vector. So you can easily compute, just differentiate. You have xy and f of xy. And if you really differentiate the other one, so this vector is exactly 0, 1, f2, ab. Okay? And then, of course, this thing is just, you can easily compute it. This is just, if you like, this vector, let's say v, maybe I should check my notation. So v1, let's say this is v2. So the normal vector can be just v1 cross v2. Okay, using this usual determinant type argument, you can easily compute this cross product. I just skip this part, and this is your normal vector. Okay, this is your normal vector. You know the normal vector, you know at least one point P, then you can easily compute the equation of an tangent line, and the equation of the tangent line, tangent plane, if we were in the one-dimensional case, if you remember the one variable calculus, now we have only the tangent line, but now we have two possible tangent lines, and the corresponding direction vectors are actually spanning or sits inside a larger space, which is called a tangent plane. Okay, so maybe I should get some piece. Okay, something like this at AB and f of AB is turns out to be something like this. Now you know the normal vector, you know at least one point on that thing, and then you can easily compute, you can easily write down the equation of the plane. Okay, okay, this is the equation of a tangent plane. Okay, we are going to use it. Fine, so let's look at the first part of the problem, part A. So it says that just locate the possible points at which the tangent plane is horizontal. What does it mean? Maybe this seems horizontal, but maybe I should sketch this part of. You will understand better, I guess. So this is of course something like this. Why I change this direction? Because horizontality means that this thing should be really parallel to that one, right? So you have some principal direction K. Therefore, in part A, it means that we look at points x y such that this normal vector is parallel to this vector, right? This is just 0, 0, 1, if you like. Okay? Therefore, this is the idea. I mean, we just we try to locate those points such that if you compute the corresponding tangent plane and its normal vector, it should be parallel to this principal direction K. Okay, so this is the idea. So somehow, but we already computed. If you look at carefully, we already know. Okay, what is this? Oh, okay, no problem. Don't panic. Okay, we already know what this n is. Then that means i.e. we should find xy in R2 such that, so therefore the first component is f1 xy. This should be 0, and also this should be 0. Okay, if we really find those points, and then if we compute the tangent plane, then the corresponding normal vector is exactly parallel to the one of the principal direction. Okay, that's all. Then this gives us the condition. So this is the condition we are looking for. Now let's check. Now just observe that. What is f1 xy? So f1 is already given. F is already given. So let's say this part is f of xy. Maybe we should specify this if you like. So let me specify. So let f of xy is, so what was it? So x squared minus 2xy and minus y squared minus 8x and plus 4y. Then if you compute, so I just skip the details, but if you really, it's not that much hard, but you can check. Sometimes I may make some computational errors, but so this is the case, and if you really compute f2, you end up with something like this. Okay, therefore if you really try to solve those equations, when this thing is 0 and minus 2x minus 2y plus 4 is 0, and if you really solve these equations at the same time, this really implies that the pair xy is exactly the point 4 and 0. Oh, what's going on? What? Did I? Sorry. Okay, as I said, I'm just getting... Oh, what's going on? What the hell? Oh. There is no control Z option or something? Okay, anyways. Okay, so we have... Okay, maybe... minus 2y plus 4. Okay, plus 4 equals 0 and blah blah. So this is the result. Fine. Is that correct or possibly no, right? So this is not true. Is that really the case or maybe not? No, I guess it's not true, right? So we should be careful. Okay, maybe. Okay, anyway, so let's try to solve it. So we have x minus y equals 4, I guess, and we have minus x minus y equals minus 2, and over here, so let's see what we get. Minus 2y equals 2, and y equals minus 1. And when y is minus 1, okay, when is minus 1, x equals 3. Okay, 3 minus 1. Okay, I guess it should do. Okay, fine. Is that correct? So that's all. This is 1 point. So as you see, we have unique solution in this case. So everything is fine. So that's all. So if you really compute the tangent plane at that point, and then you have the desired condition. So what about part B? So let's try to understand. So where is part B? What was it? Okay. So now we are looking for again a particular normal direction, so that so we have some other plane, for instance over here, some other plane with some normal vector, for instance this, but you can easily read the normal vector, 3 minus 4 and plus 2. So what we want that the tangent plane we are looking for is exactly parallel to that plane. Okay, this one. And this is possible when their normal directions are, the parallel. And that's all. So it is possible, maybe I should, let's say P1. So just note that, okay, note that the tangent plane is parallel to P1 if their normal directions are, the proportional, if you like. So something like this. Oops. Okay. Okay. That's all. Then just for simplicity, then that means that, if you like, the meaning of this statement, i.e. this n should be some kind of k times 3 minus 4 2 vector for some k. Okay. Anyways, just for simplicity, enough to observe, just for simplicity, we just look for points xy in R2 such that, so let's see, again go back, what was the definition? Minus f1 xy, then it should be equal to 2, but be careful, because of the scaling you can easily divide everything by 2. The important part is the direction, right? The length of the vector is irrelevant at this stage. We're really interested in the direction. Therefore, you can really multiply this thing in any number. Therefore, since we really want to have some 1 here, why not we just rescale it? Okay. Therefore, it's enough to look at f1 xy is equal to minus 3 over 2, and the other condition f2xy okay, should be 2. Okay. Then, as before, solving the linear system, which is okay as before. I mean, exactly the same thing. So this was the first one, but now instead of equating 0, now we have this, and the other parts something like this. So let me write it directly. Okay, this gives the point, I mean, which is hold whenever the point is xy will be this point. Again, check this, okay? As I said, sometimes I make some computational mistakes, as we almost did in the previous computation. But anyway, so this is the idea. Somehow you have to solve these equations and you end up with points. So idea is, if you really compute tangent planes at that point, tangent plane to the surface exactly at that point, then you end up with the desired types of tangent plane. For part A, it is horizontal, so it is actually right the parallel to xy plane, and we end up with some other tangent plane, maybe at this point or at that point, and this point maybe exactly the point we are looking for, and we at some other point we have another tangent plane which is exactly parallel to this one, for instance. Okay, so this is the story. I guess we are done. Okay, now this is easy. I can easily deal with this, I guess. So let's see quickly. So we are going to compute all second order partial derivatives of the given function, basically. Well, this is easy, I guess, right? Let's see. For the sake of completeness, just let me define everything suitably. So we have this and that. Then, so let's see what we have. For instance, let's compute f sub x. Now it is easy, we know how to compute it. While differentiating with respect to x, we just consider y is something like a constant, your favorite constant, for instance, 1, 5, 3, whatever. Okay, some kind of constant. And then that means we have something like this, and minus y ex. Okay, sorry. And then let's differentiate this function with respect to y. Then we have ey, but now we just consider x as a kind of a constant, again your favorite constant. And then therefore this is just e to the x. Okay, and then you can compute, for instance, this one, because we try to compute all possibilities actually, right? All second order partial derivatives. Now it is easy now, since this thing is constant, therefore it turns out to be 0 if you like. So let me write it like this, minus y e to the x. Okay, or sometimes we use the notation f1 as we did before, f12, f11. Okay, so it's the same notation. And then let's see, let me just quickly write it down. If you really compute everything with respect to y, So we have something like this, minus e to the x. What if we compute yx? Now differentiate everything with respect to x. Be careful, this is not a coincidence. I mean, this is not a coincidence. That's just a quick, maybe, just check why it is not a coincidence. You should check your notes, maybe. And then, okay, what is it? YY. And this one, and that's all. Okay. Is that correct? Fine. So part B. Part B is a little bit maybe complicated because we should be careful. We should use standard chain rule. So let's see. For instance, just compute f sub x. But now, as in the case of, one variables, right? First, you should, as you see, we have a chain rule actually. You should remember how we were using chain rule in the case of one variable calculus, if you like. And then you just differentiate it. If you like, you just let this thing t. Therefore, you should differentiate f with respect to t, and then you should differentiate t with respect to x. Okay, why not? Okay, we have something like this. Oops, we have dot, okay, not a comma or something. Okay, something like this. Then, of course, we should differentiate everything with respect to x, which gives you minus sine xy times, again, the chain rule, y. Okay. We have a minus. Okay. Okay. Maybe I should put this thing over here. Okay. And then you should once more, maybe let's differentiate everything now with respect to y. Now it looks complicated because now we should somehow use product rule, but in a very careful sense. So let's try to differentiate the first part. Maybe I should use a different color to indicate what's going on. For instance, this part. If you really differentiate with this thing with respect to y, first you have some kind of a quotient, right? Therefore, if you differentiate, you have something like this: 1 plus cosine xy squared, I guess, right? And the times, again, the same story. This is times, I'm sorry, minus sine xy, but now times x, because we differentiate with respect to y. This is the first part. Okay, so you should be careful. So then, now the second part, we didn't touch anything. Okay, we have something like this. Now plus, now we are not going to touch the first part actually. 1 plus cosine xy, something like this. But now we should compute this part by using again product rule, because we are going to differentiate with respect to y. So we have cosine xy times x times y. We didn't touch the second part. Plus, we don't touch the first part, and that's all, and times 1. Okay, you should check. I guess everything looks correct. We don't have any minus mistake, right? Anyway, so you can check it. So this is the idea. and the others are just, let's say, an exercise. Okay, so f of exactly the same computation, compute that thing, um, compute this thing, blah blah, or others, and compute the others. Exercise. Okay, fine. So what else we have? I guess this could be the last one. Okay, fine. Now we are going to use the honest chain rule in higher dimensions. So let's see. Part A. So let's try to understand the problem. So we have a function which is nice. I mean, it has continuous second order partial derivatives, blah blah. And the thing is, x depends on two things, and y depends on two things. Okay, and we have bunch of data, which means that we are going to use them somehow while computing a and b. Idea is just use the chain rule with respect to, let's say, so-called dependence relation. Or if you like, the chain. Okay, what I mean is the following. So if you look at carefully, so we start with some function like this, right? And then this function depends actually on two variables, x and y. And x and y depends actually some other two variables. Okay, so this is our chain, this is our dependence relation, and we are going to use it while computing, for instance, in part A, part B. This is our main path, our main tool we are going to use. Okay, let's see. So for instance, first one, just compute the following. For instance, del f del s. Now we should be careful, because the main idea behind this chain rule business, since we are going to differentiate with respect to s is the variable at the bottom of the chain, if you look at carefully, and there are actually a possible ways of reaching s. So one of them is this. You can use this path, or you can use this path. Okay, then this tells you the algorithm actually. So this tells you the algorithm. Therefore, to reach the differentiation with respect to s, okay, the chain rule. First, you should differentiate with respect to x. So we are here somehow, right over here. Then you should move to that thing. Plus, we have some other possible path to reach s. We should first differentiate with respect to y, and differentiate y with respect to s, and that's all. Let's compute it. So we don't have any explicit form of f depending on explicitly x and y. Therefore, we just leave it like this. Okay, no problem. But we know the explicit formulation of x. X is just e to the st, and the y is just s times exponential t. Then we can differentiate x with respect to s. So we just consider x as a variables of s and t as a function of s and t. Fine. So we have this and plus fy e to the t. Okay. And so if you really want to compute this thing at which point, when st equals 1 0, but be careful, when st is 1 0 or equivalently xy will be 0 1, right? Because when t is 0, x is 0, when s is 1 and t is 0, y is 1. Therefore, we should compute this this expression somehow. So the 0 1 times, so e to the s, e to the 1, 0. So this part is 0 times f of y. So inside we have 0 1. Be careful, f depends on x and y. And times e to the s. Oh, okay. T is 0 0. Okay, we should compute this number. So what was it? Just go back and look at the data over here, the ugly data. Okay, so what is it? Okay, here. So this is just 4. Okay, that's all. Then it's a good exercise, exercise to compute exactly the same manner. Just compute this thing. Oops. Come on. Okay. Sorry. Okay, just compute del f del t at st 1 0. Okay, this is a good exercise. So let's see. The second one is tricky actually. In part B, what was it? We want to compute okay, I'm sorry. Okay, just compute del s del t f. Okay, then okay. Anyway. Okay, fine. So we are going to compute this. But again, be careful. Be careful. Here, then we should compute where maybe, okay, it was an exercise, but anyway. So let's compute it. So del f del t is just, if you compute, it turns out to be something like this. I just directly copy from my notes. So we have something like this. Now you really want to differentiate this function. Now this is again a function. Be careful with respect to s. But now remark is the following: apply the chain rule for f sub x and f sub y. Okay, because these are also have a similar kind of dependence relation like this. Okay. Okay. So with respect to the dependence relation, so what is it? Again, f of x is actually depends on, it's a function of x and y is a function of s and t. And similarly, f of y itself is a function of x and y, and the x and y's are functions of s and t's. Very well. Okay, so let's see. Okay, then we have okay, now we are going to compute this derivative. But of course, we have this observation star, right? And then somehow we should apply what is it? Product rule, chain rule at the same time. So let's see. So first we have something like this times the second one plus, so I'm using standard product rule. Then we have e to the x, because if you differentiate e to the s with respect to s, so everything is fine. And plus, now we need something like this times se to the t plus, don't touch the first one. If you differentiate the second one with respect to s, this is just e to the t. Okay, now the hardest part. So this part. Now be careful, because now we should follow, right, this path and this path. Therefore, we have fxx, differentiate x with respect to s, right, plus differentiate fx with respect to y, okay, and then differentiate y with respect to x. Okay, now it's done. Now times e to the s plus fx times e to the x, no problem. Again, another problematic part. Now this part, this is just as before, fy x, and then differentiate x with respect to s, differentiate fy with respect to y, and then differentiate y with respect to s. Okay, looks complicated, but so this is what it is. Okay, and the plus fy e to the t. Oof. Okay, and now the final touch. Of course, you should evaluate everything at the given point, and then we get the following observations. Sometimes the notation will be given like this and evaluated at st equals 1 0, or similarly we have this. Okay, and then of course you should use the data given over here. You should use it. You can use all those things, right? Everything is given, and then you can easily compute it. Okay, and then just substitute, and the result will be okay. Probably I'm not going to compute it, just compute using the data given. Then I guess the result will be, just check it, okay? This will be the result. Okay, and that's all. I mean, this is the end actually, and okay, this is how we deal with higher order partial derivatives actually, and this is the chain rule. Okay, I guess that's all. Maybe we should stop, and this is the first online recitation activity, and see you next one. Okay, so thanks.